going over the questions, number 1, the upward force that pushes an object back toward the surface in liquids is called the buoyant force. And we should note that Joseph spelled it right. I spelled it wrong very consistently last class period. So the way it's spelled here is correct. I put OY instead of, or OU instead of UO. Okay, next one. Air pressure 101.3 kilopascals or 14.7 psi at sea level. What happens to the air pressure as you climb a mountain? It will always decrease. Why? Less air above you is basically the weight of the air. Any change in the pressure of an enclosed fluid at rest is transmitted uniformly to all points in the fluid. What is this statement called? That's Pascal's principle. And finally, linear momentum is conserved if the net external blank acting on the system is 0. It's funny because when I put this in here, I thought it said angular momentum, but it says linear. So what is required for linear momentum to be constant? According to Newton's second law, net force is changing momentum over change in time. So if net force is 0, then there'll be no change in linear momentum. Now the one I was thinking was that this was angular momentum. What do you have to have 0 for angular momentum to be conserved? The net torque, right? Because the two are analogous to each other. Any questions about the quiz? All right then. A couple things to finish up. Number 1 is in grading the homework that was due a week ago, I noticed that there were some, you can't see. There were some pretty consistent difficulties with talking about what's going on for safety in a car. And this plays into that last question we had in the quiz. So, in car safety, you know, back in the day, like the 60s, you had a seat. What could go wrong? Well, I'll tell you what could go wrong. When I was an EMT, the first call I ran, so I'm a little, trainee, come out there, so much adrenaline I couldn't speak. Truth. It's pretty weird when you can't speak. We get there and this guy had been tweaking for like 3 days, fell off the ladder, hurt his back. He didn't have a driver's license, so he jumped in his car to drive to his mother's home so she could take him to the hospital. But he fell asleep and hit a tree. Because that's what happens if you've been tweaking for 3 days and not sleeping. And he, of course, wasn't wearing a seatbelt, and so his head simply went forward until it hit the windscreen or windshield. And what happens when the melon hits the windshield? It stops really quickly. And so since it stops really quickly, you have the change in momentum from, let's say, the mass of your head times 60 miles an hour, right, that would be the momentum, to 0 in a very, very short amount of time, which means, according to Newton's second law, the net force involved, and I'm going to write Newton's second law here, force net is equal to change in momentum over change in time. You have that large change in momentum going from 60 miles an hour to 0 miles per hour in a very short amount of time. It's a really big force. And so this gentleman's nose, I actually wrote this in my patient care report, could not identify his nose. It just looked like there was hamburger going from here to here. You couldn't see any rise for the nose. Now, because this guy was still pretty high, he kept telling me that his nose itched and he wanted me to scratch it. Which, I ain't touching that. My job was to try to keep blood out of his eyes while my brother did the actual patient care, because he was my little brother was my training officer. How messed up is that, huh? Okay, so we want to be safer. So they introduced seatbelts, and they bolted those seatbelts to the frame. Yugos were still like that when I was in college. They had a one-size-fits-all. The seats weren't adjustable, and they still had the seatbelts bolted in. So when you bolted in the seatbelts, if you got in an accident, what happens? Your waist stays put, and you swing forward, which actually has as a net result your head goes faster. Probably not very good, right? So that's why we have, first of all, with seatbelts today, they're not bolted to the chassis. The seatbelts have a connection that has a spring in there, and they also, they're made so they will move freely. Right, when I was a kid, they didn't have that whole spring-loaded thing at all. You just adjusted it down and you were stuck. They move freely unless you hit the brake. You hit the brake, it locks them, and then you have a spring that you pull against. That spring you pull against makes it so it stops you over a longer period of time. Look at that equation. If the delta T is larger, what does that make the F net? Smaller. So putting that into the seatbelt mechanism so it's not just bolted to the chassis that has a spring that's going to stretch and make it take longer helps to make it safer. That's what the key was to the homework problem you had. But we go farther. We have shoulder straps. What's the purpose of the shoulder strap? Well, it's going to keep you from just bending over at the waist. It also, as a number of you point out, the more area you put that force over, the smaller the pressure is going to be on the body. Right? If you have a force that's, you have something that's just a point here and you get in a car crash, it's going to be a high enough pressure, it's going to puncture you. But if you have a plate here, you get in a car crash, it will have the same force spread out over a bigger area, and it won't puncture you, and it's safer. So having that shoulder strap helps to distribute the force bigger area and keeps you from swinging forward. It still has the whole spring mechanism to make it so it takes longer, so it's much safer. Driving without the shoulder strap is really not safe. With the shoulder strap, much safer. And then you have the airbags. Well, what's the point of an airbag? Mike, you notice Rachel is dressed up for the day and answering these questions because apparently wearing a skirt makes you answer questions better, right?
I fit in a cart before. It hurts.
Actually, yes, that's all. I do that. Okay, well, the airbags, the whole purpose of the airbag is to extend the time, just like seatbelts. So the primary airbag comes out of the steering wheel, right? You get in a car accident, what's going to trigger the airbag? What? How does it know that you've hit something? It doesn't have a brain like you do, but it has sensors. What kind of sensor can tell you you've hit something? Not pressure, but you're getting warm. You guys have seen that viral video of this old lady going across the road. Impatient man honks his horn and she hits the car with her purse and his airbag goes boom. It's because they're triggered off of acceleration. If the acceleration reaches a certain point, they assume, okay, the car can't accelerate that fast with the gas or the brake, so it must have actually hit something. So it's based on acceleration. But of course, you hit it just right, you can make it think it had a bigger acceleration for a very short time. So when it measures a high enough acceleration, it says, well, we hit something, and based on the direction of that acceleration, it will trigger off different airbags. And so the main one comes out toward you. How does it come out toward you? What makes it come toward you? Air pressure. They have an explosive in there, basically like firing a gun. It explodes, you have very rapid expansion of the gas, making a high pressure that pushes it out. You probably don't know this, but those airbags deploy at about 200 miles an hour. So if you're really close to that, it will hurt you. In fact, for really short people, there is now federal law that they have to, if you request it, disable the airbags, because for people who are sitting too close, the airbags are dangerous because they will hit you so hard. If you're, of more standard heights, then it's supposed to come out to get, like here, before you hit it, it is fully expanded, and then they have big gaping holes in the back. And so it instantly deflates, but it's going to cushion you and take longer and keep you from coming sternum into steering wheel. Instead, you'll have that big bag that's slowing you down. And of course, your shoulder strap should keep your head from hitting the windshield, like my patients did. And they have, you get an expensive car, they'll have like 19 airbags. They have side airbags. Like you get an impact on the side, a little airbag drops down in front of the window so that your head doesn't hit the hard glass, and if the window breaks, you don't have the glass all in you. There are all kinds of airbags for your safety. So I wanted to make sure we talked about that because there appeared to be some misunderstanding about the purpose of the seatbelts in the homework, and if we can't learn from our mistakes, then we all make mistakes. That's how we learn, right? Okay, a lot of time on that slide. Let's see if we can spend some more time. Bernoulli equation. Here I wrote it again the way the textbook has it. Pressure plus 1/2 D stands for density. What's the normal symbol for density? It's rho. It's the Greek version of R. And on the next slide I changed it to rho, but I wanted to show both ways so you get used to it. The pressure plus 1/2 density times speed squared is constant. So with this equation, the key aspect of this equation that we saw in the last lecture is if you have wind blowing faster, then that second term, 1/2 rho v squared, is going up. But if pressure plus 1/2 rho v squared is constant, what has to happen to pressure when wind speed goes up? If this side goes up, what has to happen to the pressure? It's going to have to go down for it to remain constant when you add the two together. So the faster the air, the lower the pressure. Remember my demonstration from Wednesday where I used the blow dryer, blew it over the paper, and the paper came up. If the paper has an upward acceleration, what does that tell you about forces? Okay, the net force is pointing up, the direction accelerated. Well, what forces were acting on that paper? First, the simple one, gravity was pointing down. Then the ones we don't think about very much, there was air pressure underneath pushing up and air pressure on top pushing down. Oh my goodness, I forgot to bring out the demonstration with the suction cup. It'll take too long to get it, so I won't do it. I'm sorry. But we had air pressure pushing down and air pressure pushing up. To make a net upward force, which one of those had to be bigger? The one pushing up. How do we reduce the air pressure pushing down? By having air blow over. And this effect is used in things like car racing. In car racing, you do things to make the air underneath the car travel quicker and giving you a lower pressure pushing the car up, and air pressure pushes it down, making it so it has what they call a downforce. And they at least say that a Formula One car at race speeds could drive upside down. I don't know if that's true, but they say that. It's a pretty big effect. In fact, we're going to watch a video about some air pressure effects in just a moment here because it's really cool. So here's something that we call a venturi. You have water going through a pipe. What happens to the speed of the water when you narrow the pipe? It has to speed up. Why? Because you have that continuity equation that says the volume per second is constant as it flows through. So if you have a smaller area, it's going to have to go faster to have the same volume through. And we learned that equation, the continuity equation last class period, that velocity 1 area 1 is equal to velocity 2 area 2. So if the area gets smaller, the velocity has to increase. So it's going faster in the narrow part. But if it's going faster, what does that say about the pressure in the fluid there? If it goes faster, the pressure goes down. Right? The Bernoulli equation says pressure plus 1/2 density times speed squared is constant. So if the speed goes up, the pressure goes down. If the speed goes down, the pressure goes up. So that means there's a lower pressure in the narrow part. And so you can see that the water level, okay, that wasn't a very horizontal line. The water level is much lower there because there's less pressure pushing up. And this is used in things like, let us say you're putting on your skirt and blouse for the day, and you want to, since you're getting all gussied up, you want to smell good. So you bring out your toilet water and you go, you walk into it, right? Yes, toilet water is the name for perfume. Well, that little aerosolizer thing is doing just this. You're blowing air, and since the air is going faster in that tube because you're blowing it with that little squirty thing, it lowers the pressure, and you have just a little tube that goes down into the perfume. The lower pressure makes the air pressure in the container push fluid up. And once it gets into your air stream, it comes out. So it's using this effect to make perfume come out. Now, probably none of us actually do this thing I just described, but it's worth talking about. Oh, that reminded me of something else I was going to talk about, something similar. Now, easy come, easy go, that's the way my brain works. Okay, so let's have our first clicker question. What happens to air pressure when wind speed increases? I know you guys don't know what different people said, but there was somebody who answered wrong the first time. This time got it right. That's learning in process. Hence my thumbs up for the learning. Daisy and Zach. I got it. There we go. 0, 3, and 4. Well, it's almost a 50-50 split. Denford, what was the correct answer? The air pressure decreases with wind speed increase. That comes from our Bernoulli relation, or Bernoulli principle. Pressure 1 plus 1/2 density times velocity 1 squared equals constant, so equals pressure 2 plus 1/2 density times velocity 2 squared. So if the velocity is faster, the pressure is going to have to drop for it to remain unchanged. Okay, now this here is just showing something like the demonstration I did last class period, but I want to talk about something different. Here in Nebraska, we are in an area that has tornadoes. What do you worry about with a tornado? Most of us would worry about our houses being destroyed. It's a common thing. A decade ago or so, the town of Halim or Halam or whatever, something close by here. How do you pronounce it? You live here. Halam? I say Halim because I think of Solomon.
I have to see how it was spelled because I don't know.
Okay, well, the town pretty much got decimated by a tornado. For people who are worried, Lincoln, it's virtually tornado proof. We haven't had a tornado here since like 1912 or something. And people believe it must be something to do with streams and maybe high spots. And you know we are on the highest spot in Lincoln right here. Peanut Hill is the tallest point in Lincoln. Okay, so what happens? Let's suppose here's my house. And inside the house, what's the wind speed? Hopefully it's about 0. Outside of the house, you have the wind blowing by with a wind speed of, let's say, 100 miles per hour. You definitely exceed that in most tornadoes. So, using our Bernoulli relation, what's going to happen to the air pressure on top of the house compared to the air pressure inside the house? Remember, pressure in plus 1/2 the density of, in this case, air, times velocity in squared is equal to pressure outside plus 1/2 density of air, velocity outside squared. Velocity inside was 0. So the pressure inside is equal to the pressure outside plus 1/2 density of air times the speed of the wind outside squared. So which pressure is bigger, the one inside or the one outside? This one here has to be bigger because it's this one plus something. Density is always positive and v squared has to be positive. So the pressure inside is bigger. Now forces, the force inside is equal to the pressure inside times the area of the roof. The force outside is equal to the pressure outside times the area of the roof. Now there's one more force. What's that one more force? Okay, gravity. So I'm going to draw that in black. You have force of gravity is equal to mg. If you take just those 3 forces, that is, if your roof was just set on your house, if the wind is going slow, you will have an upward force just due to the air, but not enough to lift it up. But if the wind is going faster and faster, you can have that force inside, the air pressure inside the house, pop the roof off. Now houses are generally constructed to keep the roof from falling down, not to keep the roof from flying up. So there is a force that's pulling down as well, but it's not so big, and if you have those high wind speeds, you can just have the roof lifted off your house. So that's one of the big problems with tornadoes. It'll pull that roof off your house. Good to know, right? Now, what could you do to make that less? Well, you could open the windows and try to get a lot of air blowing through the house, destroying everything in your house. That probably wouldn't be a good idea, right? So instead, we just go down to the basement and watch TV. Now, I think this is where we're going to have, nope, not yet. One more slide and then the video. Airplanes. Back when I was in graduate school, I thought it was hilarious to fly. I was going up to Washington State University, fly down to Southern California where I lived, and explain to the person next to me how an airplane flies. Because you normally just think, well, there's something holding it up, right? And you don't think any further than that. And what's holding up an airplane is this Bernoulli effect. The airplane's wing, first you have that rounded front side. It's rounded so it will cut the air at multiple angles. If you had the wing backward, it would cut the air sharply, and if you're just a little too steep, a little less, right? But the front is rounded so it's going to be smooth, and it's going to just cut the air no matter what angle you're at. So that's why you have the front end different from the back. And then you notice that the bottom side is reasonably flat. The top side is definitely not. So you have 2 air molecules. The air molecules get separated here as the front comes through. And those air molecules, they're sitting here, the wing comes, they basically go like this. But the one on top had to cover a much larger distance than the one on bottom did. So if that air had to cover a bigger distance over the wing in the same amount of time, what does that tell you about the speed of the air on top of the wing compared to on bottom? It's faster on top. And if the wind is faster on top, then that means that you're going to have a lower pressure on top. And so the airplane actually flies because you have a lower pressure on top of the wing than on bottom. And when you start thinking about it that way, it starts to get a little scary. We call the difference in those two forces the lift. And if the airplane slows down, then the difference in speed is not as big, and you lose lift. So you have a certain speed that's called the wing stall speed. At the wing stall speed, your upward force, due to the higher pressure on bottom, lower pressure on top, is not as big as the weight of the airplane. What happens when you reach the wing stall speed? You just fall out of the air. That's bad, right? Now, when an airplane lands, now I am not a pilot, but I believe what they're supposed to do is get down to within like a foot or two of the ground and then get the speed down low enough that they hit the wing stall and then get down on the ground and you're smooth. Right? Because you don't want to be on the ground and still have that upward lift and having to be trying to force it down. You want to get down to speed. So that's my understanding. I don't fly an airplane. You wouldn't want to fly with me. Not if you value life. Okay, what makes a curveball curve? You know, back when I was a kid, a curveball was a pitch that when you throw the curveball, you throw it like this so you have a rotation like that, and then the curveball will curve, and you throw it like this, it's going to go like that, and curve away from a right-handed batter or into a left-handed batter. These days, they call a curveball one that when I was a kid was called a sinker ball, where you come like this and your hand is going over the top instead of going around. In case you're curious, a screwball is screwy because you're going like this. You're throwing it and turning your wrist in a really uncomfortable way, which often will bend a person's arm over time. So you had screwball pitchers from the old days who would have really deformed arms because of all the stress they put curving it like that. Well, you might have seen videos of, somebody like, Christy Matheson bending a ball so you have 3 stakes in a row and it comes out, goes around and comes back, which is pretty awesome. But why is that possible? It's possible because of the crazy interactions of air. It's not exactly the Bernoulli principle. It's something that's called the Magnus force. And it's best explained with this video, which, yes, I did cue up. I just forgot that I'd already queued it up. Sound is on. If it says that it can't show it, it will just be that I have to start over.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go! Pretty awesome, right?
What day to get back in the water, dude?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off like we had no idea that was going to do that.
And this is where I come in. The basketball was subject to the Magnus effect, which affects all rotating balls or cylinders as they fly through the air. It works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way. And this is known as the Magnus effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat, but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once, and then it crashed. But the Magnus effect is making a comeback. Here is an experimental rotor wing aircraft which generates all its lift from spinning cylinders. And this is the E-Ship 1, which uses 4 spinning cylinders, that's 4 Flettner rotors, to increase its efficiency and reduce the amount of diesel it burns. So in the future, the Magnus effect may help more than just basketballs fly.
Oh, look at that go!
Now the real reason my friends from How Ridiculous were at the dam was to set the world record for the highest basket ever scored. So go check out their channel and the video and subscribe to them for more epic trick shots.
Okay, stop it.
Recently, some friends of...
One way to get it stopped. Okay, now I find that totally interesting. You're seeing physics in action, things that, I should have thought and brought an empty toilet paper roll. You can take those and you can throw them with spin and see them do this because of the Magnus effect. Because they're light, you see the effect much better than you would with a ball. And the trackball, the game I said we had when I was a kid, you have either a styrofoam ball or a hollow plastic ball. And so since they're very light, the Magnus effect causes them to do really cool things. You can really make them curve. Any questions about this? Totally down with how cool physics is? Thank you for the couple people who nodded. That's what I'm about. Okay, now we're going to change and talk about temperature. Right, that was the topic listed for today's lecture, so we better get to it. So the first question, what are temperature and heat? A lot of people, and by a lot of people I mean like more than 90%, are really confused about what heat is compared to what temperature is. And so that's something that we're going to want to figure out in the week after vacation. For today, we're going to focus on temperature. So let's get into it just a little bit. When you measure temperature, you have a kid here that's sick. He has a thermometer that's supposed to be under his tongue, sublingual. And what are you actually measuring the temperature of there? What is that thermometer truly measuring? Let's start with the ridiculous. Is it measuring the temperature on Mars? No. We can rule some things out right away. What are the possible things it could be measuring the temperature of? Okay, his tongue. Another answer? We tend to think that he's measuring his body temperature, or more specifically, the temperature by air. But in fact, what he's measuring is the temperature of the thermometer. And you put that thermometer under your tongue, and then your body warms it up. And once the thermometer reaches the same temperature as your body, then the temperature of the thermometer will tell you the temperature of your body. But you have to wait, right? Because it takes a while for it to heat up to your body temperature. How does a thermometer like that work? What happens when you stick it under your tongue? Surely you've done this, right? What happens when you stick it under your tongue? I'm asking a very simple question. I'm not trying to ask anything that's complicated. Lab next Monday is apparently going to be very enlightening to you. You'll see what happens when you put a thermometer in something. Go ahead. Somebody's going to answer. No, I should have never spoken. Well, a traditional thermometer like this, you have a bulb down here at the bottom that is filled with, well, these days, alcohol. Back in the day, it was filled with mercury. Now we almost exclusively use alcohol because, well, people are worried about the mercury being bad for you if you like bite and break it or something like that. So it's filled with alcohol. You put some food coloring in that alcohol to give it a pretty color, like blue or red are the traditional colors you see. It's just food coloring. And then when you stick it under your tongue, that blue line starts to grow. And so it'll come up to like here. Why does that blue line grow? Because for most materials, they expand when temperature increases. And so the amount they expand is proportional to how much the temperature increased. And so you just measure how much the volume increased by measuring how much it moved up that tube, and that tells you the temperature. So that's how a traditional thermometer works. Now that's not the only kind of thermometer. You can use ones that measure all kinds of different things. But now we have at least our first kind of hint at what temperature is. Temperature is something that when it's higher, things tend to expand. There are some distinct cases where that's not the case. For instance, water. Water at 4 degrees Celsius is the most dense. If you, it was least dense. Least dense at 4 degrees Celsius. If you heat it up, it will expand. But if you cool it, it will also expand. And when it freezes, it expands even more, which people know and love when they have things like their sprinklers crack because they had water in there and then it froze. And when it froze, it expanded. It was too much for the pipe. So there are some anomalies, but generally things expand when the temperature goes up. What makes things expand? Well, just think about it like this. If we were all in a little mosh pit and we're walking around like this, when I walk and I hit something, it's not a very violent collision, right? And we could end up being very tightly packed. But as soon as we start going fast, we're getting our swing on, you hit somebody, they go flying. And what does that do to the spacing between people? It's going to increase it. And that's exactly what temperature is about. The lower the temperature, the slower the molecules are moving. Because they're moving slower, when they hit other molecules, you just have these little subtle things and everything can be nice and compressed. But when the temperature goes up, they're moving faster. They have a higher kinetic energy. And so when they hit molecules, they go scattering and the space between them gets larger and larger. So temperature is actually a measurement proportional to the average kinetic energy. Now, that proportionality is pretty much exact if you have what we call a monatomic ideal gas. For other things, it's not an exact proportion, but it still is. The higher the temperature, the higher the average kinetic energy. So temperature is really measuring how fast stuff is moving. Who would have guessed that just offhand? Pretty much, I expect nobody would have guessed that temperature is just measuring the average kinetic energy. So, some things about temperature, some words. This is a page full of vocabulary. You have words, I tried to put them in different colors, like thermal contact. Things are in thermal contact when they can pass energy from one to another. What do we call that energy pass from one to another? Heat. So, heat is a word for energy passed from one thing to another. Heat naturally flows from the hotter material to the colder material. So if I touch your computer and it feels warm to me, it feels warm because heat went from your computer into me. And my sensation of the warmth was because the heat was going into me. Now, if I touched it and it felt cold, then what would be happening? Heat's going out of me. So you touch something and it's cold, heat is going out. So we can compare our temperature to something else by I touch it feels cold, and it was colder than me. I touch it feels hot, it was hotter than me. But the actual sensations are because of the heat flow. Now that makes for some interesting things like you can go out on a dock and you have this nice wooden dock and you walk barefoot and you're just fine until you stand on the flat head of a nail. And that flat head of the nail, it's not poking into you, but it burns. Anybody experience this? Okay. It burns. Why does it burn? It's the same temperature as the wood. But the wood is very poor at conducting heat. So you put your foot on the wood, and virtually no heat flows because it's really bad at conducting. Whereas the nail is really good at conducting heat. You put your foot on that, and heat just keeps on coming in. And so then you're feeling, ooh, it's hot. The wood was hot, but it wasn't transferring the heat, and you couldn't tell. Another reason why I like carpets. A carpet, you have an air barrier, and these little fibers with a lot of air, and air is really bad at conducting heat. So when you walk on the carpet, it's usually not going to feel hot or cold. It's just kind of neutral. Whereas if you have something like hardwood or concrete floors, then you have good conduction. And if that floor is cold, which it usually is colder than your body, right? Your body's sitting around 98, 99 Fahrenheit, and the floor might be at 75 Fahrenheit, it's going to feel cold on your feet. Whereas the carpet won't, because you don't have that heat flowing. So heat is a transfer of energy going always from the hotter thing to the colder thing. Now we have another transfer of energy we've already talked about. Do you remember the other transfer of energy we've talked about? I've got this, I push on it, I transfer energy. What did we call that? Force times distance? Work. So work is also a transfer of energy. But work involved motion. Heat didn't involve motion. And so we say that heat is the transfer of thermal energy. Work is mechanical energy transfer. If heat is a transfer of energy, what do you suppose the units are? Joules. Now, historically, that's not the way people understood it. Historically, people thought that heat was some kind of fluid. In fact, there was a theory of the caloric and the frigidic. The caloric was a fluid that made things hot, and the frigidic was a fluid that made things cool. And they thought that these fluids were flowing through things. And from that caloric, we have the unit a calorie. A calorie is a unit of heat. But since heat should have units of joules, right, energy, there is a simple conversion factor between the calorie unit of heat and the joule unit of heat. Were I to get there, which I clearly won't in 3 minutes, the last slide of today's presentation has the joule, the work done to show that. Okay, other words here. Thermal equilibrium. Equilibrium means equal force. Well, thermal equilibrium is not forces now, but thermal equilibrium occurs when we have thermal contact. Thermal contact means that we can have energy flow between the two things, but no energy flows. If you have thermal contact but no energy flows, then you say you're in thermal equilibrium. Since heat always flows from the hotter one to the colder one, if two things are in thermal equilibrium, that is, they're in thermal contact and no heat flows, what does that tell you about their temperatures? They must be the same. So thermal equilibrium implies equal temperature, because thermal equilibrium means bringing thermal contact and no heat flows. Okay. This one here is, I think, funny. two or more objects in thermal equilibrium have the same temperature, the zeroth law of thermodynamics actually says if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. That was a lot of words for what can really be written as a mathematical equation. If temperature 1 equals temperature 2, right, they're in thermal equilibrium, which means I bring in thermal contact and no heat flows, which only occurs if they're the same temperature, and object 2 is in thermal equilibrium with object 3, so object 2 has the same temperature as object 3, then temperature 1 equals temperature 3. Pretty obvious, right? So obvious that nobody ever thought you would need to specify that. So they came up with the first law of thermodynamics, they came up with the second law of thermodynamics, and then they're all, whoa! As they learned more about temperature, they realized that temperature was this complicated thing that had to do with, it actually has to do with the derivative, but it has to do with the motion, and then it wasn't clear that this would have to be true. And so they said, well, this is really fundamental, and so it should come before the first law. And so they said, well, what comes before 1? 0. And that's how they got the 0th law of thermodynamics. Because they didn't realize that this was an important statement because it just seemed so blatantly obvious until they understood temperature better. Okay, I am out of time. Unless this is a quick question, which I don't think it is. Nope. We will stop here. Have a great spring break.